session. Okay, this session is being recorded and it'll be posted later on the recorded presentations page for this class's webpage on my TCC Blackboard. And this Texas Network Academy Career Fair webinar is going to take place this Thursday at noon. I've got this link on here. You can see this on the bottom link on the class page. You can click on this link now if you haven't yet to register for it, and they'll send you a thing to click when it comes starts on Thursday at noon. The suggestion has been made that maybe you should dress up like you're going to a job interview in case they allow you to turn on the cameras and allow you to be seen. You never know what might happen. You might luck out and get a job or something. Okay, so I'm going to go ahead and stop sharing this and start sharing the first slideshow. We're doing 6 modules today. We're doing module 6 on network address translation. We're doing module 7 on wide area network concepts, and we're doing module 8 on virtual private networks using IPsec, which is what you would use if you wanted to use the public internet to connect 2 branch offices together, and you didn't want anybody to see your data. You could encrypt that data back and forth. Okay, so I'll click on this and then click on this. Recording audio is good. We're recording. This is good. And then I'm going to click on the first. So I joke in this course about we're going to take our $1,000 Cisco router and turn it into a $25 Linksys home router by making it do the same things a Linksys home router would do. And one of those is be a DHCP server, and one of those be a 4-port switch, and one of those is you connect the WAN port to the internet service provider and connect the LAN ports to the local people. But one of the other things that home routers do is they perform the network address translation feature because you're using a private inside address at your company or at your home location. At home, you're probably 192.168.1.1, something like that. At Tarrant County College, for example, we use the 10.0 network for our wired Ethernet stuff, and then we use the 172.16 private inside IP addresses for our Wi-Fi circuits, and that's all translated to our public address that we get. So similarly, at home, your 192.168 type address will be translated to whatever the public IP addresses you get from your internet service provider. So for example, I'm using Southwestern Bell, AT&T, and my public address is something like 99.99.99.199, something like that. But inside, I'm 192.168.1, that's something. So the network address translation function is going to translate those inside and outside addresses. So we don't have to expose our, it improves security and it conserves IP addresses. Is this going to change for me? Okay, so we're going to look at network address translation. There's a couple different types of NAT, like static, dynamic NAT. Look at the advantages of it. If it didn't have advantages, we wouldn't be using it. It's got a lot of advantages, few disadvantages. Then we'll look at the differences between static and dynamic NAT. And we'll look at what your home router does, which is port address translation, which gives you multiple inside host machines can share one outside IP address. Usually at a home service, you only get one outside IP address. And then we'll look at NAT for IP version 6, which is a conceptual thing only, because currently the CCNA objective is only be able to configure network address translation for IP version 4. We don't have to do IP version 6 translation anymore. So let's look at some characteristics of network address translation. Now here, we talked about this before in our network fundamentals class. There's a range of addresses, 3 ranges of addresses that are reserved for inside private use within a residence or company, so that the idea here is we can conserve outside addresses that there's no more IP version 4 addresses that have been allocated now. So we can use a private inside address for our inside of our corporation or our company or our enterprise or our residence, and then translate that to outside addresses. So that, for example, at home, one IP address, you can run 10 or 12 devices. If you had to pay for 10 or 12 globally unique IP addresses, your internet service would be a lot more than what you're paying, the $50 or $100 a month you're paying for it now. So the RFC Request for Comment 1918 was a proposal that set aside these private ranges of addresses. However, this 192.168.1.1 address you have at home must be translated to a global unique public IP address. These inside private addresses are not allowed to exist on the public internet. Hackers might try to spoof their source address and claim they're within your company. So all the internet routers filter them. They don't allow them using access controllers like we saw last time. So there's 3 ranges of addresses. Class A is 10.anything. Hang loose, I have attendance. Class A is 10.anything. This is what Tarrant County College uses for our internal networks. Now that's a /8 network. That's 2 to the power 24, quite a few thousands of individual host machines. We don't need that many, but we just use that range because it has the most addresses available. We use the Class B 172.16 for all our Wi-Fi access points, because when you bring in your outside devices, we can't control the virus protection and stuff like that on them. So that Class B Wi-Fi mesh network has some more restrictions, security restrictions on them, as opposed to a trusted machine, a wired Ethernet machine like a student lab or an employee or a staff machine. Those plug into the Class A wired internal network. Class C is the smallest range of networks because this Class C network only has about 250 odd available network addresses. So that's typically what home users use. Okay, even a space, these space will be good. So the main reason we're using network address translation is back in 1995, we ran into a super big crisis and we started running out of IP version 4 addresses. Before then, it was common for people within companies to not use a network address translation and to have globally unique public IP addresses. So when I worked at Harcourt, the college publishing firm in the 90s, all our machines were publicly accessible from the internet. There was no network address translation. But when we started running out of addresses in 1995 or so, they came up with the network address translation scheme as a band-aid or a stopgap workaround situation so that we could continue to use IP version 4, because IP version 6 had not yet quite been developed. It didn't really get out until about 1999 or 2000. So we can use a private IP address internally inside our system, as many as we need, and translate that to as few as just one global unique IP address to the outside world. Okay, it's not going to click for me. Maybe I can't have my mouse floating over there. Is that it? That's it. Back up, Simba back. Okay, so here's how this works. Let's say PC1. Now, do I get my pencil? Here's PC1 right here. And he wants to send something to this web server over there. And he's on the inside private network. So he's 192.168.10.10, similar to what you would be on your home network. So PC1 sends out his packet. He knows what the web server's global unique address is. DNS told him that, 209.165.201.1. So router 1 is going to receive the packet. He's going to send it to router 2, which is the border router in this situation. He's the one that's doing the network address translation. He's going to translate that inside address, inside local address, to an inside global address that's allowable on the internet. So he translates it from 192.168 to a 209.165 number, and that packet is allowed to survive through the 10 or 15 hops it normally takes before you reach a web server. So far as the web server is concerned, your address is not 192.168.10.10. We have performed rocket surgery, and we have changed your source address from 192.168 to some 209.165 number. So the web server will respond and send you the answer back to that web link that you clicked, and when it hits that R2 router coming back the other way, the R2 router will do rocket surgery now on the destination address. He'll change the 209.165.200.226 back into your actual IP address on your inside private network, which is 192.168.10.10, and you'll be able to receive your packet. So there are 4 types of addresses in network address translation. The inside address, sometimes called the inside private address, the inside local address. That's the 192.168.1.100 that your desktop PC probably has at your home internet access location. The outside device is the address of that server, the public address of that web server, Network Academy or Microsoft or Cisco.com, wherever you're going to. The local address is any address that appears on the inside portion of the network. So at home, that's all your devices that all have IP addresses of 192.168.1. something, and your router, the default gateway, friendly neighborhood router, is probably 192.168.1.1. And a global address is any address that is outside of your network. So once it's translated by your home router into whatever global unique valid IP outside address that your internet service provider has granted you, that's a global outside address. So inside local addresses, those are the addresses that I see within my network. So I can use the ping function and ping any of my inside global addresses that are 192.168.1.100, 101, whatever my inside devices are. The inside global address is the address of the source machine as seen from the outside network. So if you got the bloody eye looking at from the server on the right-hand side of the chart, he'll see me as 209.165. He'll see me as a globally unique, valid outside IP address. The outside global address is the destination, the server itself. He's the 201.1 address. And then the outside local address is the address of the destination as seen from the inside network. That's 209.165.201.1. Okay, different types of network address translation. First of all, we're going to look at static NAT. Now, static NAT is a one-to-one mapping between an inside local device and an outside device. And this is typically not used by home users, but rather by commercial users. Maybe like Tarrant County College has the WebAdvisor server and the MyTCC Blackboard server. And you need to be able to see them from an outside IP address, a globally unique IP outside address, not some inside 10-dot address that the servers actually have at our data center down at Trinity River. So since we have to, this has to be a static, permanently not changing ever mapping between one single outside address and one single inside address. Because when you're not on the Tarrant County College campus and you go to WebAdvisor or go to MyTCC Blackboard, it always appears as the same IP address. And that has to be in the DNS service of all the internet. This can't be, when we see later when we do dynamic NAT, you can get a different address at different times. That won't work when you have an inside server and you want people to come to your servers and buy your products and see your marketing and stuff like that. So this is a one-to-one thing. I'm going to consume one network address for each individual device I've got. So we need, the Tarrant County College, it needs one outside address for WebAdvisor, one outside address for MyTCC Blackboard, one outside address for the tcc.edu webpage, and so forth. So dynamic NAT is, I can use one or more than one global outside address that I've been given to by my internet service provider and assign them dynamically, randomly to my inside devices. This is the technique that's used by your home router. You have one globally unique IP address you got from your internet service provider. You're not going to pay to get the 5 or the 10 static addresses because that's for companies, not for residences. And then that one outside address will be dynamically allocated to all the different devices within your small business or your residence environment. Now, if I just do dynamic NAT without overloading, what's called port address translation or overloading, you need as many addresses as you have inside devices. But residential users don't want to pay for a lot of extra global unique IP addresses, so they're going to use a feature we're going to see here in a minute that will allow one single outside IP address to be shared among lots of inside addresses. Port address translation, NAT overload. This is the secret feature here that allows you to get one single IP address from your internet service provider, and then by using port number magic, they're going to be able to treat each computer with different port numbers, different source and destination port numbers, and share that one single IP address. To the outside world, you look like one very busy computer with lots of active ports going on at the same time. This is pretty much hardly different in practice from one single computer. You can run one single computer and run 3 web browsers on it and talk to the outside world with one IP address, and your 3 web browsers will be consistent with their data. They won't get mixed up and get their data mixed up with each other, or there won't be any corruption of data. They use different port numbers to separate that out. That's straight back from our Introduction to Network Fundamentals class on layer 4 of the transport. So port address translation just uses the same feature, but several machines can share port numbers just so long as they're unique port numbers and there's no duplication of port numbers. This is going to work fine, and this is what everybody uses at home. So port address translation is going to try to preserve the original source port. Workstations will just pick a next available port number And if two port numbers happen to conflict with each other, two source port numbers, here we have PC1 and PC2, if they happen to pick the same exact port number, the network address translation PAT function will slightly change one of them because they have to be unique, or this process won't work properly. It is limited to about, well, we have 65,000, technically we have 65,000 possible port addresses since it's a 16-bit value. But in reality, oh, maybe 4,000 is a limit. You probably don't have 4,000 devices, no. So network address translation only changes the IP4 addresses. Just the inside local address 192.168.10.10 is converted to whatever IP address you got from your internet service provider, like 209.165. Port address translation modifies both the IP address and the port number. Now notice this terminology down here. When we take my pencil, here we go. When we take a number like 209.165.200.226 and put a colon and then put those 4 digits, 2031, that's a combination of the layer 3 IP address and the layer 4 port number. So that's sometimes called a socket when you put the IP address and the port number together. Packets without a layer 4 segment. Well, how about ping requests that uses Internet Controlled Message Protocol? So they have a different method that port address translation is being used. So that's not crucial for CCNA, but I just wanted to mention that. Let's go to the next one. Okay, disadvantages and many advantages here, which is why everybody uses it. It conserves the legal, when they say legally registered addressing scheme, that's the globally unique IP addresses that you have to either lease from an internet service provider or buy a bank of if you're a huge company. So the company, if you want 5 IP addresses from your cable company, they're going to charge you a whole bunch more than if you just have 1 IP address, because IP addresses are scarce now. This conserves addresses that are on the global internet, and we use this port level magic, port number magic, so that 10 machines can share 1 global unique IP address to the outside world. Flexibility of connections to the public network, consistency. Oh, if I change an internet service provider and I get a different IP address, I don't have to change the IP addresses of all my internal company devices. That's a big hassle. You don't want to go through that. We'll just simply change the NAT code to the new address that we got. So we can easily look at, conserve our existing private IP4 address scheme, and we can change our public addressing scheme. It also has a security feature in that it sort of hides the IP addresses of our inside devices. So when I'm at school doing the lab, my workstation is like 10.144.100.100, something like that. You can't ping that from the outside world. To the outside world, I have a different address. So that means hackers that are trying to perform reconnaissance on your network and learn what devices exist by pinging every possible address, they can't do that. So it increases security. There are some advantages. It is some additional latency. This CPU process of converting your inside address to an outside address and converting it back when the answer comes back, it increases the forwarding delays. Not much. That's not much of a drawback. We don't have end-to-end addressing. Traceability, such as using the traceroute program. We can't do that through network address translation. If we are using a tunneling protocol like IP security, IPsec, which we're going to see later today, it makes it more complicated. So it can disrupt some certain services. But for the vast majority of the stuff that most people want to do on the internet, browse the web, send email, it works okay with those things. Okay, now let's look at static NAT. This is the one-to-one mapping. This is what Tarrant County College would use to establish a one-to-one mapping between some outside address that we paid for and the web advisor server, and another IP address that we paid for from some internet service provider that maps to our MyTCC Blackboard web server. So that way people can their DNS function in the outside world, you type in mytcc.edu and it will use the DNS function. They'll come up with a certain IP address. It's not a 10 dot number on our internal network. It's an outside number. And then that way you can connect through the NAT translation function that's being done by that router R2. So he says, for example, an internal web server could be mapped to a specific inside global address. So it's accessible from outside networks. The configuration is not that complicated. Step one, we're going to create a mapping between the local inside address and the inside global address using this command. Is the pencil still on? Okay, IP NAT inside source static. This is the inside address of, say, the web advisor server. And then this is the outside address that webadvisor.tccd.edu seems to be from the outside world. And then when we go to our 2 ports, we go to our port that's connected to our internal network. In this case, we have to, of course, we have to do this stuff anyway. We have to establish the port and give it an IP address. And then we have to say IP NAT inside to tell the NAT function that this is the inside network. And then we use the command IP NAT outside. On the outside port, this is probably the T1 line or the current connection that goes from our internal company router to our internet service provider. And that tells us what the outside address is that needs to be translated to that inside address. So for example, my home router would translate my outside address of 199.99.99.199, whatever it is. When that answer comes back to me, that'll translate it back to my home computer's 192.168.1.100 style address. So when this happens in step 1, the client sends a packet to the web server. The client's on the right this time and the web server is on the left. Router 2, which is your home router, will receive the packet, and he will look in his network address translation table, and he'll change that outside address to the inside address. And this process goes in reverse when he sends the answer back. So in this static NAT situation, the web server is maybe at the Trinity River downtown campus and has a fixed IP address, and it needs to appear to the outside world as a fixed IP outside address, not a 10 dot something. Web advisor's 10 dot something on our inside network. It needs to be a public IP address that's accessible to the world. We can verify this with some commands. Show IP NAT translations will show us how many translations have taken place. So in the second trace, we can see that a translation has taken place between the outside address of 192.168 or 209.165 and the inside private address of 192.168. Show IP NAT statistics will show us how many times translations have taken place. So in this case, we've had 4 translations that have taken place and 1 translation that was not taking place because the number didn't match the allowable range of IP addresses to be translated. Okay, now let's look at dynamic NAT. Dynamic NAT is what your home router uses. Dynamic NAT is going to map as many inside local addresses as you need, limit of about 4,000 really. You probably have fewer than that at home, to some global address that the internet service provider has assigned to you. So we can have a pool of inside global addresses, or we can just say all of them can do it. We're still going to have to make an access control list to allow what range of addresses if we want to restrict it or if we want to allow everybody. In a K-12 environment, for example, the children under 6th grade might not be allowed access, and the children over in 7th grade that may be allowed access, for example, and administrators. So if I just have, if I'm not using the port address translation and I only have like 5 addresses, only 5 inside clients will be able to be translated at any one moment in time. But we're usually going to use port address translation and port magic so that as a home user, you only have 1 outside global IP address. You can have as many inside devices connect to it simultaneously. You don't have to wait just because 1 device is using up that address. So to configure this, we're going to use this particular command, IP NAT pool, and make up an arbitrary name. In this case, it's called NAT pool 1. And then we're giving the range of addresses that our ISP has assigned to us from the outside world. In this case, it's from 226 to 240, so it looks like we have a bank of 14 addresses from our ISP that we're using internally. And then we're going to have an access list that permits, in this case, the access list 1 permit 192.168.00, and our wildcard mask is 0.0.255.255. So that says if your IP address is 192.168.anything.anything, you are to be permitted. And then we refer to that access list 1 in the command IP NAT inside source list 1 and tie that back to the NAT pool name. And this will make the translation take place. With the 14 available outside addresses, up to 14 internal clients can be connected simultaneously with this code. If there's more than 14, someone has to wait. Now, we still have to do the step of telling which port is the NAT inside port that goes to connect to our internal clients, our protected clients, and which port goes to our ISP or back to our home office, which is IP NAT outside. So in the dynamic NAT translation process, in this case, PC1 and PC2 are both sending packets going to a server on the outside world. So when the router R2, which is our NAT translation router, he's the one right here, he's going to check the access control list. That says ACL access control list. Are these IP addresses, source IP addresses of these two PCs, PC1 and PC2, allowed to be translated? And in this case, they were. It was all 192.168 were allowed to be translated. So R2 is going to perform the rocket surgery and change the source address of these two transmissions from these two PCs, PC1, PC2, into the globally unique IP address that was assigned from the outside world, 209.165.200.226 and 227. You just grabbed two addresses that were available and assigned those to them. Then as the server receives the packet, he doesn't think you're 192.168, that's something. That's not allowed to exist on the internet. He thinks you're a global unique address that's allowed to exist on the internet, like 209.165. Then when he sends the answer back, R2 will look in his table, his network address translation table, and see the response coming back in and change what is now. You're the destination now. Your destination address is 209.165, but that's not your address. You're 192.168. He'll change it back to that proper address so that to the left of that dash line within the internal company network, everything's 192.168. You'll be able to receive that destination reply back at your workstation. And then PC1 and PC2 receive their packets. And this process, to the right and to the left, completes over and over for every packet that you send out. Now we can verify dynamic NAT with the same command, show IP NAT translations, and it'll show us any translations that have taken place. Very useful command. If I show IP NAT translations of verbose, I can see more detailed information about the inside global, inside local addresses, and how long it took to create it and so forth. Translation entries timeout after 24 hours. So I can change that. I can change it with IP NAT translation timeout. Sometimes, I think they're going to have you do this in the lab. If you change your translation code, because in the lab they're going to have you do a couple of different types of translations, a couple of different types of NATs. To clear the translation table out, you type the command clear IP NAT translation space and then the asterisk character, and that will clear that table out of any history. And you sometimes have to do that command if you like change from static NAT to dynamic NAT in the rest of the lab, and you need to clear that out. That command will do that for you. Then we can show IP NAT statistics and see the history of stuff. In this case, we've had 47 translations that have taken place between the outside interfaces and the inside interfaces, serial 0, 1, 1, and 0, 1, 0. Dynamic NAT can also be shown if you do show the running configuration. Use this filter character, the up and down pipeline character. And if you say show running config space pipeline character and include NAT, it will only include the lines in the running configuration that have the word NAT in them. So that's a useful way to zoom in on lines. Now, port address translation is the feature that if we don't have enough outside addresses from our ISP to satisfy all our inside devices. So if I use the same exact code and just add the word overload at the end of it, that will tell the iOS to use the port address translation and use as many outside addresses as you have and add port information, make that address layer 3 IP address and layer 4 port number a socket, and you can serve all those devices at the same time and nobody has to wait. So this is what all home routers do, essentially, with them. They have one global unique IP address that you were given from your cable company, and they can have as many inside connections as your home router can handle. So in this case, we're going to configure a NAT pool like we did before. And we have the same range of addresses from 226 to 240, 14 available IP addresses. We have our access control list. The only difference really is in the third line. We're going to use the overload keyword, add the overload keyword to our IP NAT inside statement. And then we'll specify the serial ports, which one's inside and which one's outside. And this will add a little bit of extra processing power to the router to do this, but that way you can conserve and only use one outside address and have multiple inside devices being set up for it. Now in this case, PC1 and PC2 are going to share an outside global address. So when those inside source addresses of the PCs, one's 10.10, one's 11.10, when they're translated to the outside address, they're going to be changed to that 209.165.200.225, same layer 3 IP address, but their port numbers are different. One's got port number 1444 and one's got port number 1445. And so they can keep them separate, just like a PC keeps two web browsers separate with his port numbers, and we can get consistent communication. We can verify port address translation by using the same command, show IP NAT translations. And we can see whether the outside global addresses, whether they're using the same address or whether they're sharing different addresses. So looking at this print, we can see that the outside addresses, well, one's 201.1 and one's 202.129. They were given separate outside addresses. Show IP NAT statistics will show us that it's a single address for both translations. Shows us a bunch of other extra information, more detailed information, verbose information about what's being allocated. Now, NAT64 is kind of been deprecated. It was a means of being able to use a network address translation for IP version 4 to supposedly make translation unnecessary. There was a range of IP version 6 addresses that had an IPv6 private address space called unique local addresses, and it was similar to the RFC 1918. This was a workaround when IP version 6 was first introduced in 1999-2000 timeframe. It's not recommended. This is not good practice anymore. What we should do instead is we should, for the time being, run our IP version 4 legacy stuff and set up dual stack and also run IP version 6, and then migrate everybody over to IP version 6 as quickly as possible and stop using IP version 4. Okay, now I need to go to the next slide set. Sharing file, share this now. And let's talk about some WAN concepts. So we're going to look at wide area networks and traditional connectivity and modern connectivity. A lot of stuff has changed in the past 20 years or so because of the advent of much higher speed leased line connections. Look, back in the 90s, a T1 line was considered super fast. It was 1.54 megabit. Well, nowadays, a gigabit is considered more attractive. So a local area network is within a small area, like the 328 distance limitation we have with twisted pair copper cable, typically used within an organization to connect its devices together. It's owned by a home user, owned by an organization. High speed bandwidth using wired Ethernet and Wi-Fi services. A WAN connects, say, the South Campus to the Trinity River campus. Now, we can't run our own wires or fiber optic cables to the Trinity River location. We can't dig up ditches and make our own wires. We're not allowed to do that. We have to use the telephone company or other service providers' wires, cables that are already in the ground and lease them. So we lease a service from AT&T to connect our campuses together using their fiber optic cables. So WANs connect networking services over a large geographic area, like within a city, like the college, or geographically, internationally, or nationally. They're not owned by us. They're owned by internet service providers, telephone companies, cable companies, they're satellite providers. And we have to pay a recurring monthly fee to get that service. If you don't pay the fee, they're going to disconnect your service. They used to be slower than LANs. Back in the 90s, the LANs were Ethernet and they were 10 megabit, 10 million bits per second. The WANs were at the fastest you could get was a T1 line that was about 1.5 megabit, about 7 times slower. The market has changed now. We have very fast WAN services available. So to illustrate right now, we're 1 gigabit in the lab, 1 gigabit Ethernet connections in the lab to our workstations. The connection between us and Trinity River campus is a 10 gigabit fiber optic cable. So this changes the nature of the speed. You don't have to put your servers in each remote office anymore. You can put all your servers downtown. So we have our data center in Trinity River campus where all our servers are located. A private WAN is a connection that a single customer has. So if I had a private T1 line, we used to have private T1 lines between the campuses, and they didn't get to go to an internet service provider. There were our own lines. So that gave us connection from campus to campus. And the Metropolitan Ethernet technology, sometimes called carrier Ethernet, the GigaMan is what Southwestern Bell AT&T calls it. That's a private connection that's provided by the telephone company, our service provider. It's not a public connection to the internet. That's just a private connection between the campuses. A public connection is like an internet connection. Now, if you have an internet connection between a sales office in Dallas and a sales office in Fort Worth, if you wanted to reduce costs, you wouldn't also get a private connection between the two offices. You would just use the public internet connection you already have between both offices and communicate between the Dallas and the Fort Worth office using that. You would have to worry about security since everybody can see everything, but you can use what's coming up later today, virtual private network using IPsec encryption security so that people like the competition can't see that data. So let's see, we have point-to-point topology, hub and spoke topology. I think we have a different slide for each one of these. So a point-to-point topology is a point-to-point circuit. So if I wanted to connect the Fort Worth office to the Dallas office, I could lease a private circuit. In the 90s, it would have been a T1 circuit. These days, it'd probably be Metropolitan or MPLS or something like that. And get a connection, a layer 2 connection between the two devices that I can put my upper layer data in. This can become expensive if there's lots of different points used. So if there's a central office, let's look at Tarrant County College. We have our central hub is the Trinity River campus. That's where our data center is located. And then we have one single line that goes from the Trinity River to the Northeast campus, another single line that goes from the hub at Trinity River to the South campus, another single line that goes to the Northwest campus. So if anybody at the Northwest campus sends anything to the Northeast campus, it has to go back to the downtown hub, Trinity River, and then go to the campus. It's a single point of failure. It is, however, more inexpensive to provision than using, a fully meshed topology, which would be more lines to have to lease from the telephone companies. Dual home topology reduces the single point of failure. So let's say that we go to Trinity River and have 2 routers and have each of those routers have 3 lines to each of our 3 remote locations. And that way, if a line fails or a router fails at Trinity River, there's still a connection. More expensive to implement. We're doubling our telecommunication monthly rates. But if it's a situation where you must have the reliability, in some enterprises and environments, it costs us money if we lose connectivity. So we pay for the extra cost for this. A fully meshed topology is the most expensive. We're going to run one wire of each of these 4 routers at the top. We're going to run one wire to each of the 3 locations. So any one wire can fail and we have a backup route. We can sort of loop around the other way and still have the connectivity back to all the other locations. This is very fault tolerant. It's also the most expensive. Carrier connections are the connections that we get from a carrier is someone that can lease us bandwidth through a T1 line or a Metropolitan Ethernet line. The service provider may lease capacity from a bandwidth from an actual carrier. So you may use a service provider and they may be connected to AT&T's background connection. If you want 2 connections, it's advised to go to 2 different carriers. So for example, I might want to go, if I wanted redundancy, I wouldn't use both my lines to go to AT&T. I'd have one go to AT&T and one go to Verizon. That way, if AT&T has a massive failure, I still have connectivity through Verizon. So a single carrier is a single carrier connection. We have our single carrier connection to the telephone company. That's all that we use. And then we have you can have a dual carrier connection if you want to say use Verizon and AT&T as your separate ones. And that way, if Verizon has a massive failure, maybe AT&T will still be in operation. Go to your downdetector.com and see if it's working. Networks have changed over time. and companies' needs also change over time. And we're going to use a company called Span Engineering. It starts out as a small network, so it's going to use a DSL line. Now, yeah, DSL lines have been deprecated. Now we're supposed to use fiber optics. They're not repairing the DSL lines anymore in some markets. Once we grow to a campus-sized network and we move to a big building, we now have a campus area network. We're going to put a firewall in there to make sure people can come in from the outside world. We have some actually employees that we pay for, in-house IT staff to run the network. And now we add branch offices. So now we have to lease connections from each branch office to a carrier that gives us connectivity between all the branch offices. And finally, we grow to a multinational corporation, and we have connections all over the world. So I had experience with this when I worked for Harcourt Brace in the 90s. Harcourt Brace had about 100 branch offices throughout the world. We were on every continent except Antarctica. And we had a frame relay-based telecommunication network that connected all our various offices together. And today you would use virtual private networks over the internet to encrypt that data so that the bad guys or the industrial competition wouldn't be able to see your secret marketing plan for next year. Okay, WAN operation. We have our standards organizations we've talked about before. The Telecommunication Industry Association, Electronic Industry. These are trade organizations that represent the best interests of vendors and manufacturers. And if they can standardize things so they'll work with each other, in theory, they should be able to sell more products and make more profits. So the EIA-TIA 568A and B standard for that RJ45 connector, yeah, that was a standardization they came up with so they could sell more networking wires and networking devices. Today, all networking devices have that standardized RJ45 connector in it. The ISO standard are the people that came up with the OSI 7-layer reference model. And then the IEEE, Institute of Electrical and Electronic Engineers, said, oh, you dummies, using the Hicks rule of engineers, which says that the only thing that two engineers agree upon is the third engineer is wrong. So the IEEE engineers said, oh, you OSI engineers, you were wrong. You should have 8 layers because the data link layer has to be split into the MAC physical layer corresponding to the network card hardware and the logical link control layer corresponding to the software driver disk that goes with that device to shim it into Microsoft Windows or Mac OS X or whatever you're using. So these are all some organizations that have done some standards writing here. So at the layer 1, we have layer 1 to review. The 3 things that we're really worried about at layer 1 are what kind of light or electricity represents bits 0 and 1, at what rate of speed are those bits being transmitted, and how do we shape our plugs and jacks together so we can successfully make up a circuit so these guys can talk back and forth. So at layer 1, we have some optical, he's showing some optical standards here, SDH, SONET, and DWDM. This just transmit the bits at a certain rate of speed. Layer 2 protocols are, how do we encapsulate the frames that are being sent over? We're going to assemble a bunch of bits together into a frame. Just like on an Ethernet switch, we assemble a bunch of bits together and we call it an Ethernet frame, and has a source address and a destination address and a frame check sequence, upper layer data. So Ethernet is most commonly used. And for wide area network protocols, Ethernet WAN, Metropolitan Ethernet, is really so popular today. Instead of having to actually run a serial cable from some weird DSU, CSU serial T1 line and plug it into the serial port of a router and then convert all those point-to-point protocol frames into Ethernet frames, we're just going to get an Ethernet handoff from the service provider, and they're going to give us a little box with an RJ45 in it, and we'll just plug it into our network, and we're ready to go. Now, a lot of this stuff is no longer really of importance in CCNA. We're really only Ethernet based only. We don't have to do any more point-to-point protocol. We don't have to do any more HDLC. We don't have to do any more frame relay. Some of this stuff has been taken out because these days we're probably going to be using Metropolitan Ethernet handoff-based devices. We're probably not going to use that old T1 line. We're probably not going to have user routing with the serial port anymore. There are some WAN terminology terms here. Data terminal equipment, data communication equipment. I'm going to use you probably don't remember, or you weren't born yet, but we used to use things called dial-up modems, the Hayes modems that made the screeching cat's noise, and we would attach them to our PCs. So in the good old days of the 90s, I would connect to Starlink or America Online or my internet service provider using a dial-up telephone modem, like a Hayes type modem, and I would simply plug that modem into my computer. So my computer was the data terminal equipment. Terminal means end of the line. My PC, desktop PC, would be the DTE, and my dial-up Hayes modem would be the DCE. And the Hayes modem would convert my digital ones and zeros into screeching cat's analog noise that being sent over standard analog voice telephone line. These days, your data terminal equipment is your home router. Your data communication equipment is your cable modem. Sometimes the manufacturers put them all in one box. Customer premise equipment is the equipment that you own. Your home router and your other devices, you may lease or you may own the cable modem, depending on which cable modem provider you're using. The point of presence is the point at which the subscriber connects to the service provider network. So taking your telephone, your voice telephone line as an example, if you go into your backyard, there's a little gray box about the size of a dictionary that's screwed to the side of your house. And inside of that is the connection between your internal telephone wiring at your home and the wire that comes down from the pole. And where the wire comes down to the pole and goes into that box is where the telephone company's responsibility ends. You're responsible for your own internal wiring. That's a demarcation point. That separates the carrier's responsibility from the stuff that you own. If you're a business, it's the same thing. They'll run a high-speed data line to your premises at the point of presence in the basement of the building, and they'll give you an RJ45 jack, and they will guarantee everything will work up to the RJ45 jack, but they're not going to fix your internal routers and switches. If they have a problem, you have to have a guy that does that yourself or hire a consultant to do that. The local loop is the last bit of wire or cable that goes to this customer, the subscriber, the residents of the business. It's usually the worst possible slowest speed because they have very fast internal fiber optic networks. So the wiring that comes to my residence is this wiring that's buried in the ground from Kennedale to Southwest Arlington, chewed on by squirrels, and there's a pedestal over in the park. It gets flooded every now and then. And that's where the very high bit rate DSL subscriber service that I get from AT&T, I get about 80 megabit. Kind of slow compared to your cable guys. The toll network is what you're paying your monthly subscriber rate for. That pays for AT&T or any of the internet service providers to pay for all their facilities and keep them working. A backhaul network or a backbone network is a network that connects all of those central offices together, all those telephone company and service provider central offices together. So WAN devices can include the old dial-up modems. That's a legacy device. The Hayes dial-up modems are making the screeching cat's noise. Still can be used most anywhere because there's usually voice dial-up telephone lines available most anywhere. But they've been pretty much replaced by residential users, at least, would use a DSL modem or a cable modem, broadband style modems. In the commercial world, we would use something called a channel service unit, data service unit to connect to our T1 lines. This is what we would use to connect the various campuses of Tarrant County College to the other locations. Our data center used to be at Northeast Campus, and when you would go to register, you would go down to the gym, and they would give you some punch cards, and the punch card readers would be read, and then you'd get a printout of your schedule in a couple of minutes. And that was all connected back to the Northeast Campus, where we had a big IBM mainframe that did all that processing. An optical converter is used by, for example, the cable company runs fiber optic cable from there's about, I think, 6 locations in Fort Worth for the cable company. They run out to different locations in town. And then when that fiber optic cable gets to your neighborhood, they have a converter box that converts those fiber optic signals to the electrical signal that travels through that coaxial cable that actually goes into your house. Most people don't get fiber in their house. They get a piece of wiring. A wireless router, an access point, that's what you connect to a WAN provider. Some WAN providers are providing a wireless service where instead of running a wire to your house, you'll just put up a wireless tap device like WiMAX. WAN core routers are similar to the routers that we use, our little $1,000 branch office routers that we use in the Cisco Academy, and our little $500 switches. The WAN providers use much more powerful devices because they have thousands of subscribers. They use $1 million switches and $1 million routers. And I just heard in the news, there's a 6-month backlog for these super high-powered carrier routers because of the chip shortage. The same chip shortage that's causing the auto manufacturers to have to shut down their production lines because they can't get these very large-scale integrated, super high technology electronic circuits produced fast enough anymore. Serial data communication is a USB port. It's serial communication, 1 bit at a time. Before we had USB, we had the COM1 and COM2 ports like we used to plug our console cables into in the lab to go to the console port of the device, of the router or switch. Parallel communication is all 8 bits at the same time. It used to be very common back in the 80s when you plugged in a printer, like the old Epson dot matrix printers. You would plug those into your PC using a parallel port, and each character that went to the printer would be sent as a series of 8 bits over 8 wires all at the same time. But this is limited to a very short distance. When I first came to Tarrant County College in the early 1980s, one of my first jobs was wiring up our printers to printer boxes to be shared, and you can't run a parallel printer more than about, I don't know, 10 or 20 feet more than that as a problem. Serial cables can be run much longer distances. Ethernet is actually a form of serial data communication. There's only one wire pair to transmit the bits, so they're sent one after the other. And Ethernet connections over twisted pair cable are good for like over 300 feet. Circuit switched is, telephones are an example of a circuit switch network. You pick up your phone, you dial a number. It stitches together some wires and makes your caller, who you're calling, makes their phone ring. And then you can have your conversation. And when you guys hang up the phone, these elements, these circuit elements that were stitched together to make that circuit are released and they're free for someone else to use. So all communication uses the same path, the one that was initially clicked together by all those relays when you dial the call. This is by voice telephone lines and integrated services digital network, ISDN, which we don't, it used to be a CCNA objective, but it hasn't been in there for some time now because most people have dropped ISDN and they've gone to fiber optics. Packet switch communication is what you use from an internet service provider. You might not get the same path every time. He's going to use the fastest path available at any one instant in time, and packets can be stored in memory and buffered and put in a queue and sent one by one until they're received by the other workstation. So it's more flexible, it's less expensive. So Metropolitan Ethernet, multi-protocol label switching, which is not a CCNA topic, he's just presenting it here to confuse you. That's a layer 2 2.5 protocol that carriers use to encapsulate your IP packets to go back and forth. Frame relay is an old technology that used to be very popular. It's still around a lot like South America. Most of it's been replaced in the United States. When I was at Harcourt in the 90s, we used our frame relay international circuit to connect together our 100 branch offices. Asynchronous transfer mode, ATM, it was the darling technology of the 90s, but it unfortunately turned out to be difficult to understand and just too expensive. It was supposed to be advantages of it. It was supposed to be better for voice, video, and data, for streaming data. But unfortunately, about the same time that ATM came out, Gigabit Ethernet came out, and it was much more inexpensive and practical, so everyone switched to Gigabit Ethernet, and now we have 10 gigabit and further. When fiber optic cables are used, at layer 1, we have to have some means of encoding the bits, like a flash of light is a 1 and a no flash of light is a 0, for example. So SDH and SON are some standards for how we can use either expensive semiconductor lasers, ruby lasers, or semiconductor light emitting diodes to send this information over certain distances. The latest technology is called dense wavelength division multiplexing, which is kind of like using 4 different colors of light over one piece of fiber optic cable, and maybe the green light is your circuit, and maybe the red light is my circuit. It's actually not visible light, it's actually infrared light, but you could use different subtle shades of the light to send different stuff over one single piece of fiber optic cable. And they keep getting faster and faster rates over fiber optic cable. They keep running tests and getting just stupendous amounts of speeds over them. Now let's look at traditional WAN connectivity, legacy connectivity. When local area networks started popping up in the 1980s and 1990s, the companies decided we needed to connect with our other branch offices. So we would use a dial-up line with a screeching cat's Hayes modem, or we'd use the T1 and T3 lines that had already been developed by the phone company. It was originally developed, T1 lines were originally developed to send 24 voice telephone communications over one physical wire. And it turned out that because they changed voice analog data into digital bits, it was perfect for sending computer data, which is digital bits. So in America, we have a thing called the T carrier. T1 lines, 1.54 megabit. T3 lines, 43.7 megabit. In Europe, they're called E carriers. It's kind of the same technology. It's very similar to T technology in the sense that Portuguese is similar to Spanish, but not quite the same. And in E carriers, they have more channels. So they have 2 megabits instead of 1.5 megabits. They have 32 individual voices instead of 24 individual voices. So leased lines are simple. It's simple to install. And once you get them provisioned and installed, they're going to have good. They're going to usually work perfectly and never fail. The disadvantages are they're more expensive. So I mentioned frame relay. Until the early 90s, the traditional way of connecting all offices together would be, company locations would be the standard T1 lines. And this required a separate point-to-point connection between each location, each branch location and the home office, and lots of DSU, CSUs, and lots of serial ports. And frame relay came on the scene, and it allowed all these single branch office connections to be multiplexed over one single wire. So back at the home office, instead of having 20 modems, 20 DSU, CSUs, and 20 serial ports, we could do everything over one port and one router. And that made it simpler, and it made the managers happier because there wasn't such a wiring mess at the home office. So the disadvantage is it can be, when you use point-to-point links, it can be more expensive. So circuit switching is the traditional telephone lines. When you dial the telephone up, that's sometimes called POTS, plain old telephone service, a public service telephone network, PSTN. A dial-up Hayes modem, like we would probably use back in the 90s, we would use a dial-up telephone connection. And we would simply convert our digital ones and zeros coming out of our computer into a screeching cat's type of analog noise that can be transmitted through a voice circuit, an analog voice circuit. The circuit is limited to about 50 kilobits per second. That's not very fast. The other service that was available back then, it was a little bit faster. It was about 128 megabit. The author of the comic strip Dilbert used to work for the ISDN service for Pacific Bell, Pac Bell, and he was familiar with the service. It's a very mature service, very easy to get, no distance limitations like you have with DSL. And for a while, when DSL came out in the late 1990s, it was kind of hard to order it. It was such a new technology that the phone company, which is not known for their competence in the first place, had hard trouble provisioning circuits and getting circuits up and working. But they understood ISDN. You could get that. That had been around for 10 years. They knew how to handle that. Gradually, they got pretty good with DSL. So packet switching is legacy. Frame relay is a way of sending data back to the home office, and you don't have to have 10 separate circuits coming back to the home office if you have 10 branch offices. And instead of using MAC addresses at the data link layer, they use something called the data link connection identifier, the DELC, to identify if I have 10 different branch office circuits coming back to the home office. Synchronous transfer mode was a darling technology of the 90s. Instead of having 1,500 characters in an Ethernet frame, we only had 48 bytes with a fixed overhead of 5 bytes, mixed 53 bytes. It was very good for things like streaming audio, streaming video, because the packets were so much smaller. We call them cells now instead of packets. But it was just too expensive and too difficult to engineer. And the final the nail in the coffin here was Gigabit Ethernet came out and made it impractical. Now, modern days, what are we going to use? We can't use dial-up lines anymore. If I'm a small company and I want to use a dial-up line and I'm in Vietnam or something, I might need to do that. But in most developed non-third world countries, we're going to have faster connectivity options available to us. So we're going to use some type of dedicated broadband. For example, Tarrant County College is connected to the other campuses through fiber optic cables, and we get very fast speeds, like 10 gigabits. I can even lease or buy my own dark fiber and run my own network if I want to. I can't dig the dishes and put my own cable in there, but I can lease the cable that someone else has already buried in the ground. So far as packet switching, Metropolitan Ethernet, Carrier Ethernet, GigaMan is what the phone company calls it here locally. Very good service and very simple because you just get an RJ45, you plug it into your network. Multi-protocol label service is allows us to use different types of technologies. It's not a CCNA option, it's a CCNP option. And then you can always get internet broadband connections pretty much anywhere, usually from the cable company or from the telephone company. And if that's all you can get, it's easy to connect your branch office together using the public internet. You just have to worry about security, and we can do encryption with IPsec coming up soon. So Ethernet wide area networks and Metropolitan Ethernet, Ethernet over MPLS, virtual private LAN service. Easy integration. This is the killer feature. It's easily integrated with your existing networks because the service provider hands you a little box with an RJ45 on it, and you just plug it into your existing network. And the expenses and administration are reduced, and so that's what most people have gone with. If you're in an area where there's lots of fiber in the ground, like in the Dallas-Fort Worth metropolitan area, there's plenty of fiber already in the ground. Now, if you're between here and Whitney and you stopped at Blum, and you might not even be able to get a T1 line out there, or an ISDN line, it's so far in the middle of nowhere. Or in the west end of Galveston Island, you might not be able to get it. But in major metropolitan areas, it's pretty easy to get this type of service. Multi-protocol label switching, not a CCNA objective anymore, but this is a method that's similar to the old frame relay that would tag, this packet came from the Northeast campus. It would tag another packet. This packet came from the Northwest campus as it sent it back to the Trinity River core campus, and then the Trinity River router would make the forwarding decision and send it back and forth. And it has a lot of advanced features. Now for internet-based connectivity, we have wired and wireless. So if I want to bring in a fiber optic cable like we do from the South campus back to Trinity River, or you want to bring in something from the telephone company or from the cable company at your residence, it's going to bring in some wired option to your house. So DSL, cable connections, optical fiber-based networks. Wireless options, they don't have to run wires. So if I get a cellular 5G hotspot, I don't have to any wires run to that location. If I get the Hughes-based satellite internet service, and I'm in the west end of Galveston Island, in the middle of the desert in the southwest, I can still get internet connectivity. Now on the negative side, wireless signals can be affected by interference. From like if there's a thunderstorm, it might cut off your connectivity. Okay, DSL is the connection that uses when they first started doing the T1 lines back in the late 40s and early 50s, they discovered that the frequency response of a cable pair was a lot more than just the audio. The audio is just the 0 to 4 kilohertz. That's all the bandwidth you need to make the voices where you can understand the user and recognize who the caller is. So what DSL did was it used the upper frequencies up to about 1 megahertz, and it put the DSL data in there. If you've ever had a DSL installation, they give you little filters you plug into all your devices so you won't hear any of the squealing from the upper layer modulation that's carrying the digital data. And so the rates you can get depend on how far it is from you to the central office, what shape the wiring is in, and so forth. So when I was on the old traditional legacy DSL, asymmetric DSL, which is common for residences, I was getting about 5 megabit. That's enough so that if someone's watching a streaming television show and I try to go to a website, they start yelling because the television show starts stuttering and scrolling and buffering. But when the telephone company started phasing out the old legacy DSL, I got the very high bit rate DSL, which is about 80 megabit. And that's plenty of bandwidth for several TV shows to be watched at the same time. And someone can go on the internet and it doesn't bother the people watching the TV shows. So DSL works by running one single telephone line to the subscriber. And this telephone line carries both the traditional analog voice signal as well as the digital signal for the internet data service. Once you get back to the telephone company central office, which is the other line working, okay, the digital service link aggregator module, it could be at the central office, it could be at a pedestal out in the field somewhere. That will split your service into the telephone analog, copper wire, and the digital internet service that for example, that my telephone company maintains to the internet, so I can have my internet service. The old standard DSL, which I'm not on anymore, used something called point-to-point protocol over Ethernet, where you had a username and a password that would log you into the DSL network, and if you kept paying your bill, you would be able to get that connectivity. And that functionality was not in my computer, it was in my home router. I went into my home router and I configured the screen, and I said PPP over Ethernet and my name and password that they gave me, and I was able to get connected that way. That's router PP over E client. If you were someone in the field with a laptop, you could put the same software on a laptop and use that to directly communicate. Cable technology uses, the cable company runs optical fiber out to your neighborhood, and then that optical node, that transceiver we mentioned earlier, converts the ones and zeros in the fiber cable to electrical ones and zeros going over the coaxial cable to your residence. And then at your residence, you have a little splitter. One wire goes to the TV, set-top TV box for your 500 channels and nothing to watch. And then the other splitter wire goes to your cable modem, and the RJ45 plugs into your home router and connects to all your local devices. This is a shared system because the optical fiber is sharing everybody in that neighborhood. The different types of optical fiber are in some areas you're not getting optical fiber at the residence, fiber to the home, where fiber reaches the boundary of the residence, and you either get an actual piece of fiber coming into the house, or you have an optical transceiver and you get a piece of electrical cabling coming in. Fiber to the building, the fiber comes to maybe the basement of the building, like an apartment building, and then we'll have individual copper for the individual subscribers. Or we might have fiber to the node or fiber to the neighborhood. And I joke and I call the one fiber to the press, which is the technology companies bragging about their fiber optics. They never can seem to get installed properly. Of course, fiber can deliver high bandwidth because you can get much more bits per second in a fiber optic cable than you can get into a copper cable. Okay, some other wireless-based broadbands. Municipal Wi-Fi. Some municipalities have put in internet service. Example is when Hurricane Katrina came to New Orleans and wiped out a bunch of the city. A bunch of volunteers put up a municipal Wi-Fi network on, phone poles and light poles, so that people could log into the internet for free and send email messages telling their relatives that they were okay. Another option is cellular. So if you have a cellular phone or cellular hotspot, most phones you can turn on a hotspot feature and have your laptop computer communicate with that. If you're in a location like in the southwest desert of Arizona, and there's no cable or wire anywhere, no DSL, no cable, but there are overhead satellites. So you can use satellite connectivity like the Hughes system, and some other vendors are offering this now. And then WiMAX is a system where you can put up a tower somewhere and wire it into the internet, and then offer everybody within range of your tower, which is a few miles. WiMAX is very similar to, I'm going to call it Wi-Fi on steroids. It uses radio frequency transmission. Hold on, I got to track attendance. Vocal on, okay, good. I can. You can use WiMAX to provide service. For example, at the west end of Galveston Island, there's a WiMAX service provider that you can get internet service if you lease a beach house for a week and you still need your internet connectivity. But it's too far out away from the city of Galveston to get good cables and wires to get service. Virtual private networks are a technology where we can use, if we have a branch office in Dallas and in Fort Worth, and we could run a private line between the two of them and then have internet connections because they both need to contact their customers and trading partners. That's kind of double the cost. Well, if we're connected to the internet anyway, let's just use the existing internet connection and use that to do the connection between the Dallas office and the Fort Worth office. But we don't want our competitors to see our secret data. So what we can do is establish a virtual private network and encrypt all the information between the offices, and only the offices have the secret keys or the shared public-private keys, so nobody else can see the data. So that way it saves us money, gives us security, and we can simply add capacity when we don't have to add a bunch of expensive infrastructure. Supported by any internet service technology that you can get. Two types of VPNs are site-to-site VPN, where we configure the router at the branch office in Fort Worth and the router at the branch office in Dallas. They both go to their respective ISP connections. And all the machines at the Fort Worth and branch offices, Fort Worth and Dallas branch offices, they don't need any VPN code in them. Now, what if it's remote access? What if I'm a salesperson at a sales convention and I need to dial into the home office and get that secret marketing plan to present to my guys? Well, in that case, I have to have the VPN software on my laptop. Or as an example, if you use a browser to connect to the bank and see which transfer money, that is encrypted, and you essentially have a virtual private network connection with the evil Chase Empire or whatever bank you're using, and then you can do your transaction. Nobody else can go in there and steal the money from your bank account. Some connectivity options, we kind of talked about this before. We could do single home connection to the ISP using one link. So you have one link to one ISP. Now, I've heard of some people that are real nerds. They have one connection to the phone company, and they have one connection to the cable company, and they bridge them together and get faster bandwidth. That's dual homed. If we did this with a company, we might have one connection to AT&T and one connection to Verizon. And if either one of those companies goes out, unlikely that both of them would go out at the same time, we could still have some connectivity to our clients and to our customers. Multi-home is connecting to two separate ISPs. And dual multi-home is two wires to each of two separate ISPs. So any one wire cable can be cut, any one ISP can fail. It's more expensive, but we have more guaranteed connectivity. So let's consider what should we take into comparison when we want to look at the advantages and disadvantages of what solution we're going to use. Cable residential is shared by everybody else in the neighborhood. You may have slower service in the evening when everybody's going to Netflix. DSL is kind of distance sensitive. You have to be closer than about a mile or two from the telephone company's central office. Fiber to the home is better because the fiber comes straight to your house, and the cable companies and the phone companies are both busy pushing, in my neighborhood in Southwest Arlington, they're pushing fiber optic cable through all the neighborhoods here. So they'll be able to soon offer fiber to the home with that. Cellular mobile option, you have to worry about coverage, although they've gotten better with the coverage. That way you can turn on the hotspot feature on your cell phone and get a dedicated hotspot and get internet service access within your house. Municipal Wi-Fi is not that popular because if you're in an area where they offer it, it's usually less expensive and higher speeds. But the for-profit corporations have been pretty successful by doing a sort of a divide and conquer operation against the 50 state legislatures. And they went to all the legislatures and used language like, this is not a level playing field. The municipalities should not be allowed to compete with the for-profit corporations because they have advantages. They can use their existing water pipes and drain pipes to put fiber optic cable in. So they got it outlawed in most states. So for example, when Katrina came to Louisiana and the volunteers put up the municipal Wi-Fi, the big for-profit corporations went to the Louisiana legislature and had it outlawed right away because they didn't want to have to compete with free. How do you compete with free? Satellite option is limited capability, but if you're in the middle of the desert, it's the only thing that you can use. It's typically more expensive and has more latency. Okay, I think that's it for this one, and then we're going to go to do one more. Share this, share files, share 8, and we're going to get a little bit more detail about IPsec and virtual private network. Go to the next slide, please. There we go. So virtual private networks are used over an existing internet connection. We want an end-to-end private connection between, say, a home office and a branch office. It's transported over a public network, and you can just assume that anything on the network can be viewed by anybody. But we're going to make it private. We're going to encrypt the data. Anytime the data is present and it's not within our branch offices, it's encrypted. So anywhere on the public network, it's going to be encrypted, and no one will be able to see it. So the benefits is it's going to save us cost. This looks like the same one we saw earlier. It's going to save us cost because we only have to have one lease line to the internet. They don't have a separate private lease line to the other branch office. Has high security because we can use as many bits of encryption as we want to. It's scalable. I can add branch offices. I can add bandwidth, just like call my ISP and increase the bandwidth. And it's compatible with most any type of broadband technology that you could use. Okay, we had this before. Site-to-site VPN. There is a VPN router or gateway at each location. And in site-to-site, there's one router at the home office where the skyscraper is. And that encrypts all the data within the building and sends it to the outside public network, untrusted network of the internet. The branch office could have its own VPN gateway, and all the machines in the branch office will use that. But in this case of this diagram, we've got we have the home router is doing the VPN translations. Sometimes the cable companies want to charge you extra if you're using VPNs because you're using it for a business purpose. And it's supposed to be best effort only residential use for those. They want higher rates for business use. So the client computer, in this case, that uses laptop, he doesn't have to have VPN code installed on them. Slide change, okay. Okay, now let's say the salesperson is dialing in from a hotel or something where it's not his router, it's not his home router. So he could put the VPN software, like Cisco Easy VPN is a software product that installs on a laptop, and then you can dial into a Cisco-based VPN router gateway that's present at the home office. And you'll be able to get into the home office and see that secret marketing plan you wanted to get to. So I can, as an enterprise, I can manage the VPNs myself. In this case of Tarrant County College, we have our own VPN service that we offer to our staff and employees and teachers where they can dial in and be connected to the internal network. I could go to a service provider and use a software as a service and have the service providers create and manage the VPNs themselves. They'll probably use multi-protocol label service to do this. And that, like frame relay, the old frame relay, our traffic is separated from the other traffic from other customers, so they can't see our data. So remote access VPNs are how we dial in to the enterprise from some remote location. I can use a clientless VPN connection if I make the line of business application the user, the employee needs to use based upon web pages. Like for example, when you come in to go to My TCC, it's a web-based interface. You come into Web Advisor, it's a web-based interface. You don't have to install special software on your own PC, you just have to have a web browser. So I can have the IT software people at the home office make everything that the salespeople in the field have to use based on a web transaction application. That way it just goes through a web browser and we'll turn on the secure socket layer, TLS, SSL, encryption connection, just like you do when you go to the bank, or just like you use when you go to Amazon and you put in your credit card number. That's all encrypted. You don't want everybody else to get your credit card number. Client-based is that salesperson that's in the field where he can install like Cisco AnyConnect software on his laptop, no matter where he is, and he can connect to the home office. So in that case, the secret encryption keys are present on his laptop. He can run any software, any proprietary software that the company is using, like their proprietary sales software. So secure socket layer uses, you can run pretty much any application on the PC. It's typically used by you can run any web browser based on the desktop PC or laptop PC. It uses the secure socket layer or transport layer technology. With IPsec, I can run any application that would run over an IP-based network. With the secure socket layer, it has to be a web-based application. The authentication strength is stronger with IPsec. It's okay with SSL. It's good enough to protect your credit card information. Encryption strength with IPsec is very strong, up to 256 bits. With SSL, it can be up to 256 bits as well. The complexity of the connection on IPsec is more complicated because we have to either install the VPN client machine on your host laptop, or we have to install it in your home router. And if you're away from home, you can't do that. With SSL, there's no complexity because all you need is a web browser, and everybody's got a web browser device. So with SSL, any device with a web browser can connect to the home office. With IPsec, only maybe specific devices with specific application circuits on them, programs on them can connect. Okay, we talked about site to site. We're going to run a VPN gateway both the home office and the branch office. The two routers will do the encryption between each other, so the only thing that appears on the internet is encrypted traffic, and you don't have the key. You're a bad guy. You're the black hat guy. You can't see the data because you don't have the secret key. The secret keys are only possessed by the routers at the home office and the branch office of the authorized offices. GRE over IPsec is if you don't need encryption. This used to be, we actually used to do a lab on this, but they removed this. This is concepts only. GRE is a way of tunneling from a branch office to a home office. If you don't worry about encryption, you can use GRE. Now you can turn on encryption using IPsec if you want to, but if you don't need the security and you can save a little processing power, this is an option for this. So what we're going to do essentially is take our passenger protocol and put it in a GRE packet and then transport that to the remote office. This is a technology we used to use in the 90s when we had Novell IPX SPX, Novell network servers that wanted to talk to each other over different branch offices. We would take those Novell IPX, that's the passenger packets, and they would put them in an IP packet, which the service providers would easily provide to us. So GRE over IPsec, in this case, the branch office and the home office would be connected over the tunnel. The internet will carry IP packets easily. It won't carry other stuff. It won't carry encrypted traffic. You have to encapsulate it if you want to do that using something like IPsec or VPN. Dynamic multi-point VPNs. If we add more sites, Cisco. This is Cisco marketing fluff. We can add a feature to use generic routing and encapsulation, the multi-point feature, and have multiple branch offices using a hub and spoke technology, and be able to connect with the other branch offices as well as the home office. So in IPsec, we have the sort of virtual tunnel interface. The tunnel interfaces exist. It's a passenger pigeon protocol. It gets encrypted in the plain old. We can't encrypt all our packets going over the internet because then the internet won't be able to look at our destination IP address, and its routing tables won't be able to form the routing table lookup process and forward that packet properly. So the outside part, the public part of the packet, has to be unencrypted with legitimate, regular unencrypted IP addresses, source and destination addresses. But we can encrypt the inside parts, so going between our private networks, between the South Campus and the Northeast Campus, for example. Service providers can also provide this by, this is software as a service. They're going to do this service for you. They're going to set up, like much in the same day, old days where they would set up frame relay, accounts between 10 branch offices coming back to one home office, so we didn't have such a wiring complexity. And they can offer this as a layer 3 VPN or a layer 2 VPN. We're not going to see the video. You can look at the video on your own time. So IPsec is an Internet Engineering Task Force standard. How can we set up secure communication over a public untrusted network? So we talked before about confidentiality, integrity, availability, the ability to authenticate that it actually came from a certain origin, non-repudiation. And then we're going to use the Diffie-Hellman, which in the South I like to call Dixie-Hellman. This is a way of using a public and private key pair to initially establish secure communication between two sides, which because it avoids us having to send a secure shared symmetric key back and forth where someone might snoop it. So we're going to use a Diffie-Hellman to exchange some public and private key pairs and generate up a shared pair between the two parties where we don't actually have to send that secret shared key across the wire. And then we're going to switch because public-private asymmetric keys are very slow to encrypt and decrypt. But symmetric shared secret keys are very, very fast. So we're going to use asymmetric to get the key across and then switch to shared secret key for our fast processing of whatever transaction that this user is wanting to do. So IPsec, it's not bound to, it's kind of like, this is like the Chinese menu, one from column A and one from column B. We can choose whatever IPsec protocol we want. We can use whatever confidentiality we want. You can use DES, triple DES, whatever we want. We can use whatever we want for integrity, like MD5 is what we use for integrity of our enable secret class. We can use any kind of authentication we want to, any means of exchanging the keys, any Diffie-Hellman exchange key sequence we want. So first of all, we'll choose either authentication header or encapsulating security protocol, or both. If I just use authentication header, that means I'm not encrypting my user data. If I use encapsulation security protocol, that means I am encrypting my data. It's going out over the internet, for example, which I'm using. If I only use authentication header, I don't need confidentiality. If I use ESP, that's confidentiality and authentication. So confidentiality means that only the authorized users get to see the data. You have confidentiality when you log into WebAdvisor because you're the only person that knows your password. Nobody else can see your grades or change your course schedule. So in general, the longer the key is, the harder it is to break. The shorter the key is, the easier it is to break. Back in the 90s, 40 and 56 bits were enough. These days, we want to use 2K, 4K, we want to use bigger keys because the technology has gotten to the point where they can be broken more quickly. The object is to use enough bits to where a determined attacker cannot get to it in less than 3 years or something where it wouldn't be useful to them. So the old DES used 56 keys. Oh, that's right. The encryption version for Russia and Cuba used 40 keys because it was considered an armament and we didn't want to export it to the communists. But 56 keys is a laughingstock now. That's just ridiculously easy to break in 2 seconds. So triple this is 56 bits, then 56 bits, then 56 bits, triply encrypted. AES has some different bit lengths up to 256 bits, and SEAL is 160 bits. There's all sorts of different, there's many different encryption standards that you can use. So you can pick one from column A and pick one from column B. We want to make sure the data hasn't been changed. So I can run an MD5 signature like we do with enable secret class and make sure it hasn't been changed. This is very similar in concept to when we put that frame check sequence on the end of an Ethernet frame. And when the Ethernet frame has been transmitted, he does the hash of the frame, and then the receiving workstation recalculates the hash, and they should be the same. If they're the same, the data has integrity, hasn't been changed. If they differ in any respect, the hashes will not match, and he'll discard the data. Two methods is a pre-shared key, or we will use digital certificates, like a public-private key pair. So pre-shared key is I have to key the value into each pair manually. If I'm setting up 2 routers, I'd probably key the secret key into each router individually. But RSA is digital certificates, and that's better because we don't have to go and travel to each one and share secret keys across that untrusted bandwidth. So Diffie-Hellman is the traditional method. This is, for example, the method used when you do hypertext transfer protocol secure, HTTPS to chase.com, and you don't want everybody to know your password. You don't want everybody to steal your money from your savings account, or you don't want people to go to Amazon and use your credit card number and order stuff for them. So Diffie-Hellman has some groups. Some groups have been deprecated, 1, 2, and 5. They're don't have enough bits. We should use 2,000 bits at least. No video. And oh, that's it. That's it. Okay, good deal. So guys, don't forget about the Thursday webinar on the career opportunities that are available here in the Dallas-Fort Worth area with some vendors that are actually hiring people right now. They're looking for early career people that have CCNA certifications, which you'll be able to have when you finish this course. We'll have covered each and every objective that's on the CCNA test. And if you're interested in getting out the job market there, listen to what these hiring managers have to say. What are they looking for? What should you do? They are, I don't know if they're going to allow you to turn on your camera or not, but it probably wouldn't hurt to dress like a job interview and put your best foot forward. And if they can turn on the camera, they can see you. And maybe they'll like you, ask you to come in for an interview. Okay, hang loose. I'm going to stop recording.